Hello, welcome to iTech Labs. My name is Stan Gilinji. I'll be able to take you through the Diffie-Hellman algorithm, and I hope you have watched our previous videos where we are discussing about OS security architecture. You have discussed about the hybrid crypto systems. We also had a look at an RSA algorithm, how an RSA algorithm works, and now we want to have a look at Diffie-Hellman algorithm, which is a key exchange algorithm, which is it's part of PKC algorithm and mainly used to share the session key. Remember, we say that in SKC you use the same key to encrypt, the same key to decrypt, but that key is shared using key exchange algorithm, which is one of them is the Diffie-Hellman algorithm. So please follow this and be able to have a look at the previous videos so that you can be able to understand better in regards to the relationship between this session, this lab, and the previous one that we have been able to cover. So Diffie-Hellman is a key exchange, a foundation method for cryptography that allows two parties to securely share a secret key. And this secret key, we say that it is one that you use in SKC communications, where you want to use the same key to encrypt, the same key to decrypt. So it was proposed by Whitfield, Diffie, and Martin Hellman in 1976. So this is a method that's particularly useful for establishing secure communication in protocols like SSL and TLS. So the math behind it is more of modular exponential, but some few tweaks of it to ensure that you're able to generate the same session key. And if you see from this diagram here, we're able to see that in RSA we have the private key and public key. The same here, we have the public key and the private key. And so the public key is used to encrypt the information, private key is used to decrypt the message. And you can use the public key to verify the signature and private key to sign. So this is the RA side. RA side of shared secret key. So you can see the key, the shared secret key is generated based on these two parameters. That is a public key, both public key, and then RS private key to be able to generate them. So how does an RS Diffie-Hellman algorithm works? So the basic behind Diffie-Hellman is to enable two parties to generate just a shared secret key, meaning at the end of the communication, they should have the same key. You want to encrypt a message, you want to share a message to encrypt a message, you want to use key number 5 to encrypt, and you want to generate the key number 5 every time you'll be able to decrypt that message. So the math aspect about it is that the both parties agree on two large prime numbers. We say that prime numbers are very critical in cryptography. It means that both parties they agree, meaning that it's a handshake protocol. Every time you connect to a server, they agree on those fundamental parameters for communication, and those plays a key role in generation of key. So those prime numbers, the both parties agree on them, meaning that both P and G are known by the both sender and the receiver. So in this scenario, RS will be able to know the prime number and the generator G. So the idea is that the prime number and the G, the greatest common divisor they should share is 1. So for instance, you can select 5 as a generator, and let's say 23 as a prime number. If you look at the properties of 5 and 23, the divisors of 5 is 1 and 5. 23 is 1 and 23. So the greatest divisor they share is 1. So then the generator should be less than the prime. And they can actually be left as fixed values. So these numbers can be public and do not need to be kept secret. That means that they are actually published and you can be able to reuse them. But then there's a risk of reusing those if you have very low generators, meaning that you have a low prime number. Then it becomes easier for someone to guess what is a possible secret key that can be used to decrypt that message. The next step is that each party selects a private key, which is a random number. So the random number key, RS will select a private key A, and then Bob will select a private key B. But there's a condition of selecting these private keys. So the idea is that once you select it, in the next communication, you can select any other key, but it must be typed up to this condition of the prime numbers that is here. The generated keys here, the generated private keys should always be less than P. should always be less than P. So it means that if you use 23, as your P, then the secret key is between 1 and 23. So that shows you that an attacker is able to determine the key if you use a very low prime number. So that you need to use very large numbers so that you have so many possibilities. When you have the attacker must be able to do all the tests, and so many tests for them to derive the key. So each party computes their public key, but you can see here we are saying that Aris computes her public key. So the Aris public key is computed in this scenario here, and that public key for Aris is generated. You remember we said there's a generator that they agreed on. It is raised to the power of your own secret key, mod P. So it means that they agreed on the generator, and also they agreed on the P. Yeah, they agreed on those values. Then Bob computes his own public key. He gets the generator, he raises to his own private key that he selected, mod P, to generate the public key. So ideally what you're saying here is Aris cannot deny having generated the public key because the public key is actually based on her own private key. Whereas Bob on the other side cannot deny having generated the public key because the public key is generated based on his own private key, which is B, that he selected, or he selected randomly from that communication or that selection process. After they do that, they have agreed the prime number, they agree on the generator. Aris selected her own private key, Bob selected her own private key, B. Aris computed her own public key based on her own private key. Bob generated his own public key based on his selected private key. Those public key are exchanged. Remember we said that the public key are used for encryption process. So they exchange the public keys. So Aris sets her public key to Bob, and then Bob sets his public key to Aris. So how is the shared key computed? So once Aris received the message, you can see the shared key is computed based on this scenario. So this is Aris will receive Bob's public key, and then Aris will raise it to the power of her own private key, which is A, mod P. That will generate the session key. On the other side, Bob does the same. Bob receives the public key of Aris. Bob raises that public key to his own private key, which is B, mod P. They should be able to have the same shared secret key. If you find that the key is different, then it means that key was altered during the transmission. Or that will refer to as man in the middle attack. And those are some of the main limitations of this algorithm. So this is a combination of how it works. I think I'll be able to show you how it works. Both generate those values here. They agree on my private key, the generator, and the P. And the result, and they exchange that. You receive, they both exchange the public key, get my public key, and then use that and raise it to generate the shared session key. This is an example. So let's look at this example. So in this scenario, we say that we select the prime numbers to be 23 and the base with the generator to be 5. So in the first step, we say that Aris select a private key, and we say that the private key selected should be less than 23. So it can be larger than 23. So in this scenario, you can select any value for the private key. So for this example, we choose 6 as a private key for Aris, and 15 to be private key of Bob. Remember, they can choose any key. They can use 7, they can use 8. It doesn't matter whether it's it's a prime number or an even number. It's any number, so long as it is less than P. The second step, we say that they both generate the public keys. So Aris will generate his own public key, and Bob will generate his own public key. But we say that the public key is generated using this scenario. You have the generator, you raise it to the power of Aris private key, mod P. So you say 5 power 6 mod 23. So you get us that value, mod 23. So it means that the public key of Aris is 4. So on the other side, Bob can create his own public key. He have his own generator is known, it's 5. His private key is 15, mode P, which is 23. So it means that he's able to derive his public key as 19. So they actually exchange. So it means that this key 19 will be used by Aris. This key number 4 will be used by Bob to generate the session key. So once they do the key exchange, Aris set the public key to his public key 4 to Bob, and Bob sets his public key to 19 to Aris. So they both can create a shared secret key. We say that for Aris used Bob's public key, which is now 19, that he received from Bob. He raises to the power of 6, mode 23. So that gives you 2 as a shared session key. Bob on the other side will get Bob Aris' public key, which was generated as 4, raises to the power of 15, mode 23. Bob should be able to get the same key. So it means that that key number 2 is a shared session key that can be used to encrypt the message and decrypt the message, but it is never shared as key number 2. It is shared using a key exchange algorithm, and that's a PKC algorithm. So this key is consumed in an SKC algorithm, and that will refer to as a shared session key. So you can see that both Aris now have the shared secret, which they can now use in a symmetric for encrypting. And the beauty of the Diffie method is that even though the key exceeds the public keys of our insecure channel, the shared secret key remains secure due to the difficult creating that discrete algorithm. But we have said that then you must be able to use very large prime numbers and also ensure that your G satisfy the conditions, and also ensure that you are in the encryption process or in the writing of your code, ensuring that instead of assigning the key secret, the private keys, you should be able to your system should be able to randomly select the private key, so that if this communication you have communicated, then in the next session the system should automatically select a new private key. Security of Diffie-Hellman, a key exchange, I think we have seen that is an ability of doing the raising something to the power, then mode P. It becomes very difficult to reverse back if you use very large values of the secret key, which has derived from the P, which should be less than the key. But you are saying that the man in the middle attack is possible. An attacker can intersect the public key during the key exchange, and then impersonate each party and establish a separate key. So that's why you need not to use things like the hash function to ensure that you're able to tell, or digital signature, you're able to tell that that key is modified or not. Yeah. So that even if you're receiving the key, public key, what is the integrity of that key? Is it a valid key or is it a modified key? So no authentication. The Diffie key does not authenticate the parties involved, which is why you should implement it with a framework that provides authentication. So you cannot use it alone. So you must have implementing a framework that is also able to employ the aspect of authentication. Some application areas, I think these are some of the things that I'll be able to highlight for you here. In SSL, in email security, in blockchain technologies. So these are quite a variety of. Anywhere you are dealing with the SKC algorithm, there will be a key exchange algorithm that is enabling a user, the sender and the receiver, to share the shared secret key. Thank you. That marks the end of this lab of Diffie-Hellman. I hope you have learned some few maths about it and how it is used. And wish you that you'll be able to view the previous coming channels, so we can be able to show you how it's actually implemented using various programming language like Python and also C++ or any object-oriented language. I'll be able to take you through the practical aspect of those key concepts that you have discussed. Thank you.